a position vector is basically a vector that goes from the center to a certain point. So let's say I'll just scroll down. So I'm going to draw a vector in 3D. So that means if we're working with vectors in 3D, we're going to have a y-axis, x-axis, and another axis, which is known as your z-axis. What we normally do is we put the z-axis going vertical, and we flatten out the x and y vectors. But it can be produced in any direction because it's in 3D. So you can flip, you can switch the z, the x and y. You don't have to. There is no normal actually, but the fundamental is normally I would put z on my what would look like the y-axis, but it's now in the z plane, and you can see that looks like a 3D shape. So the three-dimensional system of coordinates, basically the first thing we're going to have is the location of some position vector p, which will have the coordinate x, y, and z. And we can see we got the z over there. I'm now going to label this one x and this one y. If I have to locate the position of this vector, it means that I'm extending from the center up there. And that would be a position vector in 3D. How does this actually plot on the plane? It means that if I have the x component, which would be, so let's suppose I go firstly x and y. And let's say x and y is a and b. Let's say this is equal to p, a, b, c. Let's start with a and b. So I'm going to go a total of a down and b this way. On this plane, you can see that it ends up at AB on the Cartesian plane. That's the Cartesian plane, XY plane, right? But it's the other way around. So this is actually BA because B comes first and then A. All right. So I should label this differently. This should be in reverse. This will be A and this will be B because I said A comes first and then B. Now I'm taking this point and I start lifting it, right? I start lifting the point, a total of C. So I take this point now and I'm now lifting it up. And I lifted a total units of C to that point there. So it was there and now it moves there, a total of C up the Z plane. And so if I move that point all the way up from here till here, and preferably in line with it as far as possible, it's going to go up to C and it ends up over there. So I've got that, and then the whole thing lifts up until there. And you can see that's in 3D. So for visual purposes, that's actually what's happening with vector P. I can call this vector A again. And if I have the same vector somewhere else, it'll be A. And if it goes in the opposite direction, it will be negative A. And the same rule applies. And if I have double and half, etc., it will all apply as well. And we can also call this a displacement vector. A displacement vector in 3D basically has three components. So the example we have here is we have the point P137, and we're given a translation of the vector to the point Q538. So this would be a displacement vector would actually be a vector that describes how a vector would move from one point to the other. Okay, so displacement vector in 3D needs to have three components. An example is we start off with P, 1, 3, and 7. And we're saying that it translates to the point Q538 by the displacement PQ. And how do we get the answers? 401. You can see it's 5 minus 1 gets me 4, 3 minus 3 gets me 0, and 8 minus 7 gets me 1. How does this look visually? Visually, if this is 137 over here, and x is equal to 1, so that means technically this would be maybe here at 1. It would have a y component of 3. This is not accurate. And it would be moving up by 7. Such that if we take those 2 points and we lift that point up, it would end up there. Now, if that's the case, and it lifts up all the way till P, I'm now going to take that vector, the same vector, and I'm now going to move it 4 units to the right, but I'm keeping the 3, and I'm going to move 1 up. I'm not moving in this direction. So that means I take this point and I move it 4 units to the right. So if this is 1, it's going to be 5, which is like way out. But let's say it moves here. And then it moves 1 up over here. And I've taken the same vector, which means I would keep the same magnitude and direction. But this would end up at Q538. So that would be 5x, 3 on the y, which is actually, if I go down, it's in line with that. But it's 8, it's above here. And now I've got a displaced vector by that amount there. All right. Notation, we use lower cases like a and b, and parallel vectors obviously have the same vector, a and a, b and b, and fractions of it. And we did scalar, and we now combine displacements by adding and subtracting. Okay, so let's have a look at this next part here. I'm going to scroll down again. Combining displacements by adding and subtracting. Starting at point A, we make a displacement AB of, so we're given a displacement of AB of 4, 2, followed by a displacement of BC, 3, 7. And these are displacement vectors. Starting at some point A. Okay. Starting at point A, we do this. What is the result is the question. What is the result of displacing a vector by this? The overall displacement means that if we on a plane, again, let's say I go into just a positive space here, and I'm starting at the central point, I'm going to call it A, and I travel 4 units to the right and 2 up. That's going to be 1, 2, 3, 4, and 1, 2 up. Then this over here will be creating vector AB. Okay, and then vector BC goes 3, 7 after that. So 1, 2, 3 plus 3, and 7 up from 2 goes to 9. 3, 4, 5, 6, 7, 8, 9. And that ends up over here. So that'll go all the way till there. And that'll be vector BC. So now I got vector AB and I got vector BC. What has happened to my point A? It ends up with a resultant vector at C. And the resultant vector at C has the x coordinate of 7 and the y coordinate of 9. Basically, we take 4 plus 3, which is 7, and 2 plus 7, which is 9. So what do we have here? We have a point A, which got displaced to a point C. But we also have a vector AB and a vector BC and a vector AC. So we have points and we have vectors. And each vector has an x and y component. And we notice that the resultant vector is AC. So we can even write AB, because then this point will be B. AB plus vector BC equals the resultant vector AC. In other words, 4, 2 plus 3, 7 must equal 7, 9. And so we're combining displacements by adding and subtracting them. Based on that idea, we can also look at, if I bring the negative of AB, it's going to be equal to BA, which is going in the opposite direction, actually, like that. This arrow always goes right. It's just to state that it's a vector. So we don't ever put the arrow backwards. Okay. So the negative of AB is the reverse, BA. We've seen it already. And then the examples, etc. So when we find the magnitude of a vector in 2D, we use Pythagoras' theorem. But if we want to find the magnitude of a vector that's in 3D, then that will be something different, right? So I've got a vector in 3D now. I want to find the magnitude of a vector in 3D. What we do is, suppose I've got a vector 2, 1, 3. When we're finding the magnitude, what we do is we basically have two lines like this. That becomes the magnitude. And we take each component and we square it. And then add it. And then square root it. 2 squared is 4. 1 squared is 1. 3 squared is 9. And that's equal to 4 plus 1 is 5 plus 9 is 14. And so the square root of 14, final answer there. And that would be the...
So it's the same.
So it's the same as Pythagoras' theorem.
Yeah.
Same idea behind that, yeah. And that would be magnitude. If I'm given vector P is equal to 5, 0, 8, and I'm given vector Q is equal to -1, 8, and -3, and the question says find the magnitude of P plus Q. Find the magnitude of P plus Q. Then all I have to do is add it first to get 4, because 5 minus 1 is 4, and 0 plus 8 is 8, 8 minus 3 is 5. And so the magnitude of P plus Q is the magnitude of 4, 8, 5, which is 4 squared plus 8 squared plus 5 squared square rooted. So that's 16 plus 64, which is 70, 80, plus 25, which is 105. So the square root of 105 would be the magnitude of that vector in 3D. The next thing is a unit vector. What is a unit vector? The unit vector is of size 1, because sometimes we have vectors which may be a fraction of 1 or 1.5 or 3.5, but we use the unit vector as a vector of 1 to sometimes represent other vectors with a coefficient in front of it, or a factor of it in front of it, or some kind of multiple or multiplier, you could say, in front of it. So unit vectors basically any vector of magnitude length 1. Any vector length is equal to 1. The notation of a unit vector is this little bit of a hat. And that's the unit vector of A, of vector A. So in other words, if I have a vector over here, and I know that the magnitude of the vector is equal to 4, right? Then the unit vector, which is always equal to 1, because by definition it has a magnitude of 1, is going to be a quarter of the magnitude of A. Because a quarter of 4 is 1. And we don't have to write it sometime like that. We can also just write it like this. Quarter of the original vector will come to 1. And what that means is that we can divide this into 4 equal parts. Then that part over there, just that component at the start, is a quarter of A in the same direction in parallel, and is my unit vector. So to find the unit displacement of a vector in particular directions, we first have to find the magnitude of the displacement and then divide the components by the vector of the vector by the magnitude. So if I have a vector in 3D, which is given as P1, P2, and P3, then the corresponding unit vector is going to be equal to a fraction of it. P divided by the magnitude of P, P2 divided by the magnitude of P, and P3 divided by the magnitude of P. And all of this is a vector. If I can just write it all in one big column vector, x, y, and z. Now, how do we get this? If I go back to this notation that we did here, I can see that this was the magnitude here. And if I bring the quarter into the bracket, I can rewrite this as the unit vector is actually equal to A over 4 by the looks of it, right? It's the magnitude of it divided by 4, like that. And that became that unit vector. This is supposed to be not half, sorry, it's supposed to be a quarter here. Okay. Because it's 1, 1, 1, 1, all equal parts for this. All right, let's have a look at an example. And we want to find, the question says, find the unit vector of the square root of 5 and 2. So what we have to do is first find the magnitude. So we find the magnitude of that first. Square root of 5, 2, which is going to be equal to square root of 5 squared plus 2 squared square rooted, which is 5 plus 4 square rooted, which is 9, which is 3. And so that's the magnitude. But we know that a unit vector is, so we can even write and say, but a unit vector is equal to, the word unit means 1. So that means we have to take this vector and divide it by 3 to get the unit vector, which means, therefore, that a third of the original vector is going to equal my unit vector, or 1.
Oh. So how would you write that?
And so I would distribute this, because it's off, I can multiply. I would distribute the 3 into the bracket. And I would take that 3 and divide it into each component. So I would take square root of 5 over 3 and 2 over 3. And that would become my unit vector. And so this is a unit vector. Now let's have a look at it in 3D, right? Let's have a look at the question in 3D. All right, we got points A, B, and C are such that AB is equal to 3, 4, 1 on the XYZ plane, and BC is equal to 11, negative 2, negative 1. Find the unit displacement vector is the question. Find the unit displacement vector. In the direction AC. So the solution would look like this. Well, AC is the resultant vector formed by AB plus BC. That's the general. A to B, B to C, so AC is the sum of the two. So AC is AB plus BC. Now AB is basically 3, 4, 1, and BC is 11, negative 2, negative 1. And when we add it up, we get 14, 2, and 0. And this is going to be vector AC. Now we want to find the unit displacement vector in the direction AC. We have found the vector. So step 1, let's find the magnitude. All right, so when you get the unit vector protocol, find the magnitude. So the magnitude is going to be equal to 14 squared plus 2 squared plus 0 squared square rooted. And that's going to be equal to the magnitude of 14, 2, and 0, which is going to be 196 plus 4, which is the square root of 200, which is 10 root 2. This is the magnitude. The magnitude of a unit vector, by definition, is 1. This is not 1. So we have to divide it by itself. So step 2 is step 1. If I have to call it step 1, find the magnitude. Step 2, divide it by itself. And then use that back in the original vector over here. And so that means I have to take 1 over 10 root 2, and this would be the unit vector, the unit displacement vector of 14, 2, and 0. Divide each component by the magnitude of it, and I can then distribute that in there, or I can leave it like that. And if I distribute it, it'll be 14 over 10, which is 7 over 5, with root 2 at the bottom. I can go 2 to 1 over 5, so 1 over 5 root 2. If I put 0 over that, it'll just be 0, and so that could also be known as the unit vector. They're both equal, and so that would be my unit vector. That's my original vector, that's my unit vector. And on the 3D plane, if I'm on the 3D plane again, I'm just going to draw a quick sketch here where that's Z. I could just draw lines everywhere. Actually, I could draw a line this way, down this way, and then 1 in this plane. In the 3D plane, if this is going 14 to the right and 2 up and 0, actually 2 to the down, and it's going to be 14 on the X, let's say, and you're going to go 2 on the Y, but 0 on the Z plane, then that vector is just going like till there in the 3D plane. So the unit vector, remember, is the portion of that vector. The portion of that vector that'll equal 1. And so this vector will land at that X and that Y and 0 up to ensure that the length of it is 1. by simply dividing the original vector component by the magnitude initially to get a multiple of you can say something like that, to get that final answer there. All right, so there's a basic introduction to 3D vectors.